Alright guys, how's it going? Today we're going to talk about photons and photon energy. So what photons are is they're basically just little packets of light that are often referred to as particles of light. Okay, and we're going to learn that the energy of a photon is going to be directly proportional to the frequency of the electromagnetic radiation. So really quick, we'll just see. You can write that E is proportional to F, where F is a frequency. Sometimes you'll see frequency written as V like that. So either F or V both mean frequency. Okay, so let's start out by looking at our electromagnetic spectrum. Right, so most of you guys are probably familiar with this. We got our radio waves here on the left, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. So we should notice here that our longer wavelengths, right, our bigger lambdas, lambdas the symbol we use for wavelength, are on the left, and our shorter lambdas are on the right. So some of you may know this, some of you may not, but wavelength and frequency are inversely related. So while we have a big wavelength, we're going to have small frequency here. And when we have a short wavelength, we're going to have a bigger frequency. So radio waves have the smallest frequency, and gamma rays have the biggest frequency. So we just go left to right, we should see that the frequency is going to increase. Okay. So the next thing I want to do is just to talk a little bit about where this idea of the photon comes from. And for that, we got to visit the early days of quantum theory, and we'll talk about the scientist Max Planck. So here's Max Planck. Based on when he was born and passed away, we know that he did most of his work in the early 20th century, late 19th, early 20th century. So Planck was a German physicist, and what he proposed was that all forms of matter come in little bundles called quanta. And more specifically, when we're talking about light, right? So these bundles are like little particles of matter, and light quanta is known as a photon. Okay, so you might be thinking right now, is light a wave, right? Because we describe it by wavelength, frequency, or is it a particle, right? Because now you told us that there's a photon, which is a light particle. So which one is it, right? Is light a particle or a wave? And it turns out that light actually is kind of both. So in some ways, light exhibits wave-like properties, and in some ways, light exhibits particle-like properties. And this is really known as the wave-particle duality. So if we go, we're really just getting on the very edge of the weirdness of the quantum world, but I don't want to go too into that yet. So like we said, light actually has both wave and particle properties. De Broglie, so another French physicist, he discovered that electrons, right, which we up to this point have really just considered little bits of matter, also exhibit wave-like properties. So again, that quantum weirdness that we're running into. But for right now, let's just remember that light and all electromagnetic radiation exhibit wave and particle properties. All right, so the next thing, let's finally get to the energy of a photon. And looking back to our friend Planck, he actually developed the following formula which relates energy of a photon to its frequency. So this is E, which is energy, is equal to H, which is a constant, actually not named after Planck, and V here is the frequency. So, and the energy is going to be measured in joules. Planck's constant is going to be 6.62 times 10 to the negative 34th meters squared kilogram per second. And the frequency of the electromagnetic radiation is going to be measured in hertz. And this formula is also sometimes referred to as the Planck-Einstein relation. And you may see it written like this. E is equal to hc over lambda, where c is the speed of light, and lambda is the wavelength of the electromagnetic radiation. Again, speed of light is measured in meters per second, and the wavelength is measured in meters. Okay?